Hi guys, welcome to chapter 15. We're going to jump around a little bit and we're going to cover section A and C, and then we'll cover B on a later day, okay? So we are talking about thermal energy, which is one of the specific kinds of energy, and it basically relates to the movement of the particles of all matter, okay? So we talk about a couple of different terms when relating to thermal energy, and one is temperature. Temperature relates to the average kinetic energy of the particles of a substance. Okay, so if you think about having a pot of boiling water, okay, those water molecules are moving a certain amount. That's kinetic energy. You stick a thermometer in there, and it's going to measure the average kinetic energy of those particles, and it's going to be translated into a number, and that's what we read. Okay, the higher the temperature, the faster the particles are moving. Okay, so the higher the temperature means more kinetic energy. All right. Now, thermal energy is the total kinetic energy of the moving particles. It's not just the average, it's like an amount of all of the particles. So if I have a small cup of boiling water and I have a large bucket of boiling water, they'll read the same temperature, but the bucket will have a much higher thermal energy because there's more particles. Okay, so it's a total read, a total measurement of the particles. Okay. We get these things known as thermometric properties, and it's just any property that consistently changes due to temperature, and density is one of them. We can kind of predict what's going to happen with the density of materials as they heat and cool down, except water. We'll get to that. And there's this thing known as thermal expansion, which is a thermometric property. Most substances actually expand when they heat up, okay? And the reason for that is the particles are moving more. And as they move more, they take up more room, okay? And you see this in metals. I'll have another video with some examples of that. You see this in gas. As a contained gas heats up, it expands for lots of reasons we'll learn about. But thermal expansion is that kind of predicted observation of things getting bigger as they heat up, okay? Which would mean they'd get smaller when they got colder because the particles will slow down and get closer together, okay? Most things we see that, except for water. Water actually becomes less dense when it freezes, okay? So as water heats up and it becomes water vapor, it follows the principle, it expands and does that. But when you freeze water, it doesn't contract. It actually expands and becomes less dense. And as Christians, we believe that's because we need water to float. Because if water sunk, if the surface of a pond froze and that water was actually more dense than water, it would sink. And then the surface would freeze again and it would sink. And it would keep doing that until the entire pond was frozen solid and it would kill everything inside of it. So water is different than the other substances, and we can't really explain it scientifically. It's a God thing. All right, so we've got these three temperature scales. This last one is Fahrenheit. Can I move myself out of the way there? We're going to talk about the history of these scales a little bit. The initial scale was the Fahrenheit scale, and the rest are kind of based off of that partly. But in order to come up with a temperature scale, we needed these things known as fiduciary points, and it's basically two known points, okay? And the common ones used now are the freezing point and the boiling point of water, okay? Those are known points. Back when this was first developed, this guy named Daniel Gabriel Fahrenheit, that's where it came from, he developed the first thermometer using the freezing point of water and the normal temperature of humans, okay? So it had nothing to do with the boiling point of water. And he chose 32 degrees right here as the freezing point of water because that's the coldest it got in his hometown. Like, it's so arbitrary. Eventually, it was changed to be a scale from the freezing point of water and the boiling point of water. So on the Fahrenheit scale, water boils at 212 and it freezes at 32 degrees, okay? From there, we went to this guy named Anders Celsius, and that's for the Celsius scale. This is the metric system. He set out to not discover, but to design a scale that had a gap of 100 degrees because it's much easier. The gap between these two numbers is not very mathematically easy. It's not consistent, okay? So Andrew Celsius took the freezing point of water and the boiling point of water, and he separated them by 100 degrees, okay? But the interesting thing is he set the melting point as the 100 degrees, and the freezing point was the 0 degrees. I have no idea why. It doesn't make sense. After he died, another scientist came in and actually swapped it. So we've got the boiling point of water on the Celsius scale is 100, and the freezing point of water is 0. Well, then this guy, William Thomson, also known as Lord Kelvin, came up with a different scale. And this one is more related to the Celsius scale than it is the Fahrenheit scale. It's based on this concept of absolute zero down here. Okay, so he just shifted the scale down. You can see that the boiling point of water and the freezing point of water is still separated by 100 degrees. Okay, but instead of talking about absolute zero as a negative number, he set that as 0. Okay. And absolute zero is this theoretical concept. It's impossible to attain, but it's this theoretical concept that if you took enough thermal energy away from a substance, there'd be no more kinetic energy. The particles would not be moving at all. And so that would be absolute zero. That'd be 0 degrees Kelvin, okay? Which is false. It's impossible to achieve, which we're going to learn about in just a second, okay? But I kind of like this one right here. This is a good one. Oh boy. Come back. No. Oh. Did you hear about the guy who was frozen to absolute zero? He's okay now. Get it? 0 degrees Kelvin. Okay. At least that was kind of funny. This is not funny. This is really difficult stuff, this idea of thermodynamics, okay? So thermodynamics is the study of thermal energy and heat and how they relate to work, okay? Heat we're going to learn about in section B, and very simply, heat is just this idea that warm things move to cool things. So something is always warming up. You can't really make something cold. So if you put ice in your hand, it doesn't make your hand cold. What it's doing is it's removing heat from your hand, okay? And your hand is heating up the ice. We'll talk more about that, okay? But that's what heat means. There's this other concept called entropy that's very complicated and definitely something that is in much more advanced physics courses. The easiest way to explain it is that it's the universe's constant movement towards chaos, okay? So matter is constantly spreading out and becoming random as a system. Now, that doesn't mean that matter doesn't get organized and become solids ever, but when that happens, it means something else became chaotic. So entropy is just this description of the randomness and the spreading out of matter, okay? We have 3 laws of thermodynamics. The first law is pretty easy because we know it as the law of conservation of energy. It just states that energy can't be created or destroyed, only transferred, okay? So that one's okay. The second law is not too bad either because it's related to the definition of heat. And it just basically states that heat flows from warmer to cooler objects. If it goes from a cooler to a warmer object, it requires its own set of energy. Work has to be done to do that, okay? And along with that is this concept that overall entropy is always increasing. That randomness and that spreading out, that disorder of the matter is always increasing. So it's said that our universe is expanding because of that, okay? And then finally, the third law of thermodynamics is it kind of just goes to disprove the idea of absolute zero. It's by definition, it says the entropy of a solid at absolute zero is 0 because there is no movement. It can't get spread out anymore, but it's not possible because for something to reach absolute 0, it would mean that there would have to be something colder than it for that warmer substance to go to. Does that make sense? I know it's difficult. We'll watch some videos on that. All right. A and C. See you later.